Okay, the first question is, let Q to be a positive real number. Prove or disprove the following statement. If Q is irrational, then square root of Q is irrational as well. Okay, so if Q is irrational, square root of 2 is irrational. It's a bit hard to prove. Okay, but we know a statement is equivalent to its contrapositive. Okay, so its contrapositive is if square root of Q is rational, right, then Q is rational. Okay, so if A then B, the contrapositive is if not B then not A. Okay, if A then B and if not B then not A, they are always equivalent. Okay, so now we prove if square root of Q is rational, then a rational number can be written as an integer A over another integer B. Okay, and B is not 0. Okay, so square root of 2 is A over B, where A, B are both integers and B is not 0. Okay, then Q is equal to square root of Q squared, right? So it will be A squared over B squared. Okay, so that's why Q is A squared over B squared, then Q is rational. Okay, then Q is rational. So you prove it by proving it's contrapositive. Okay, you prove it by proving it's contrapositive. Then, problem 2. Use mathematical induction to show that the sum of the first n odd positive integers is n squared. Okay, so the first n odd integers. Okay, so what is the first positive odd integer? It is 1. Okay, so here I means the first. The first odd number is 1. Then the second odd integer is 3. Okay, the third odd integer is 5. The fourth odd integer is 7. Okay, then the ith odd integer is 2i minus 1. Okay, it is 2i minus 1. Then you want to show the sum of all the first n positive odd numbers is equal to n squared. Okay, so here the sum for I from 1 to n, 2i minus 1 is equal to n squared. Okay, you want to show this equation is always true. Okay, you want to show this equation is always true. So for mathematical induction, you need to show two things. Okay, you need to show the basic step, okay, which means, so basically we want to show the sum is equal to n squared is true for all integer n. Okay, you want to show it's true for all integer n. Then you need to show when n is 1, it is true. Okay, you need to show when n is 1, it is true. Okay, then when n is 1, it is true. You can easily show it because you can just do substitution, right? You can just substitute. Excuse me. You can substitute 1 for n. Okay, you can substitute 1 for n. If you substitute 1 for n, the left will be 1. Okay, the left-hand side of the equation will be 1. The right-hand side of the equation will also be 1. Okay, so basically you show this equation, the sum is equal to n squared. You show this equation is true when n is 1. Okay. Then the inductive step is you assume when n is k, it is true. Okay, then we try to prove it is also true for k plus 1. Okay, we assume when n is k, it is true. We try to prove it's also true for n is equal to k plus 1. Okay, so it's just like the domino effect, right? Like a domino effect. So you push down the first one, then the second one will also fall down, right? Then the third one will fall down. Then the fourth one will fall down, right? So when every domino falls down, right, it pushes the next one down. Okay, so that's just like the inductive step. When n is equal to k is true, we try to prove when n is equal to k is true, then n is equal to k plus 1, it must also be true. Okay, then when n is equal to k plus 1 is true, then obviously when n is equal to k plus 2, it's also true, right? And so on and so forth. So if we can prove this part, okay, if we can prove this part, we can show that it is true for all, right? It is true for all n. Okay, so we can assume when n is k, it is true. Okay, so the sum for I from 1 to k to I minus 1 is equal to k squared. Okay, this equation you just need to sub. Okay, you just need to sub k for n. Okay, so we assume when n is k, this equation is true. Then when n is equal to k plus 1, okay, when n is equal to k plus 1, so now the sum, okay, now the sum is for I from 1 to k plus 1, okay, to I minus 1. So it's when n is equal to 1 plus when n is equal to 2 plus when n is equal to 3, etc. Okay, and as you can see, it has two parts. Okay, it has two parts. The first part is for I from 1 to k. Okay, for I from 1 to k to I minus 1. The second part is when I is k plus 1. Okay, is when I is k plus 1. So when I is k plus 1, you just sub k plus 1 for I. Okay, you just sub k plus 1 for, sorry, you just sub k plus 1 for I. Okay, then this first sum, right, I is equal to 1 to k to I minus 1, right, this part, it is exactly k squared, right, because just now you already showed that, right, just now you already showed that. Okay, then the 2k plus 1 minus 1, that part, okay, that part is 2k plus 1. Okay, so you put them together, it is k squared plus 2k plus 1. Okay, it is k squared plus 2k plus 1, which is k plus 1 squared. Okay, so when n is k plus 1, the left is equal to right. The right is k plus 1. Okay, so this equation is also true when n is equal to k plus 1. Okay, so here the inductive step, we assume when n is k, it is true. Okay, we prove that when n is k plus 1, it is also true. Okay, so for mathematical induction, as long as you have proved the basic step, you have proved the induction step, then the statement is true for all n. Okay, then the statement is true for all n. So this is the second question.